So we're going to cover one section from chapter 20, which is about electrochemistry. And electrochemistry is oxidation-reduction reactions. So what we have to cover here is how to balance redox reactions. So just as a very quick review, oil rig, oxidation is loss of electrons, reduction is gain of electrons, oxidation is an increase in the oxidation state, reduction is a decrease in the oxidation state. And so when we have a redox reaction, we have an oxidation occurring and a reduction occurring. And what's a little tricky about these is the mass has to balance and the charge has to balance. And in order for that to happen, we have to have the same number of electrons being lost and gained. And so some redox reactions can be balanced the regular way by inspection, and you just look at it and figure it out. Others are almost impossible to balance that way, and so there's another method called the half reaction method, and that's what this section is about. We take the equation and we break it into two half reactions, one oxidation, one reduction. We balance those separately and then we add them back together. So that's what we're going to do. So steps for doing that. The first step, actually, I think is optional. Assigning oxidation states and identifying what's oxidized and reduced. Now, that might be necessary in a more complicated reaction, but in the ones I'm going to give you, it's not. So we can jump directly to separate the overall reaction into two half reactions. We balance each half reaction first with respect to mass, and we have a specific way we need to do this. We need to balance everything but hydrogen and oxygen first. And then we balance the oxygen by adding water where needed, and we balance the hydrogen by adding hydrogen ions where needed. This is for balancing in acidic solution. It's an aqueous acidic solution. And so we can add water wherever we need to balance because the whole reaction is occurring in water, and there's water everywhere. We can balance the hydrogens by adding hydrogen ions because it's an acidic solution and there's plenty of hydrogen ions around. Okay. After that, we balance each half reaction with respect to charge. The charge does not have to be 0 on each side, but it needs to be the same. It could be -2 on each side, -5, whatever. It just needs to be the same. And we do that by adding electrons. What's going to happen is one of these reactions will have electrons as reactants, and one will have electrons as products, because one is gaining electrons and one is losing electrons. So after we get the two half reactions balanced, then we have to look at them and make sure that we've got the same number of electrons, so that if the first one's losing 2, the second one's gaining 2. And so sometimes we have to find least common multiples and multiply all the coefficients and blah. Then we add the two half reactions together and cancel out electrons and anything else that can cancel. And things should be good, but we should always verify at the end. Okay, so let's do a simple example. And over here on the side, I've listed the short version of the steps. So balance the redox reaction in acidic solution. We have hydrogen ion plus chromium, making hydrogen gas plus chromium ions. So I need to separate this into two half reactions. Again, we're just going to ignore this first one. I think we got plenty of practice with oxidation states earlier. So how do I break this into two reactions? Well, this one's pretty simple because there's only two reactants. So one reactant will be the reactant for one, and the other will be the reactant for the other. So I'm going to make two equations here. And so one of them will be hydrogen reacting, and one of them will be chromium reacting. And so the hydrogen ion is going to react to form one of these products, and I'm just going to pick the one that's most like, right? Because hydrogen ion couldn't possibly become chromium ion. So it must be H2 gas here. And then the other one is down here. Any questions? Just split it into ions. Didn't do that. Split it into two reactions. I took one reaction and split it into two reactions. These are happening simultaneously, but I'm going to look at them separately. So next I balance with respect to mass. So this first one, there's only hydrogen. And so I'm going to balance that. I have two hydrogens here, and I can just put a 2 in front of the H plus and get that one balanced. And the second one, chromium, and chromium is already balanced with respect to mass. Balancing with respect to mass means, do I have the right number of atoms of each element on each side? And so I didn't even have to get into this priority list here. Then I'm going to balance with respect to charge. So my first reaction here, on the left side I have a total of +2 charges. And on the right side I have a total of 0. It needs to be the same on both sides, and the only thing I can do to fix it is to add electrons. Electrons have negative charges, right? So if I add 2 electrons to the reactant side, 2 negative charges and 2 positive charges add up to 0, and then the product side is 0 also. This is because this is the reduction half reaction. We're gaining electrons. The other one is the oxidation. That's where you lose electrons. And the charges are going to tell us what to do. Here I have 0 on the left and +2 on the right. And so to make those equal by adding negatives, I will add 2 electrons on the right side. So I have chromium, total of 0 charge over here. I have chromium 2 plus 2 electrons, total of 0 charge over there. Everybody okay? So this is the reduction reaction, half reaction, and this is the oxidation half reaction. These are happening simultaneously. When we look at the overall reaction, we don't see where the electrons are going, because they're just passed off from one thing directly to another, and so they don't show up in the overall reaction. And that makes it hard to balance them because we can't see them. So when we pull the half reactions apart, then we can show the electrons and make sure that we have the right number of each. So the next step, number 5, make the number of electrons equal. I've got 2 electrons here, and I have 2 electrons there. They're already equal. Good. Step 6, add the half reactions together. So I'm going to take these 2 half reactions, and I'm going to add them together. I'm going to put all the reactants together on one side, and all the products together on the other side. Kind of like the reverse of what I did up here, except I messed around with them a little bit. I have 2 electrons on the left and 2 on the right, and so those cancel out. Because this reaction loses 2 electrons, and those 2 electrons are gained by this one, and so these don't show up in our final equation. Yes?
So we're never going to have electrons in our final equation because
Correct.
they should cancel out.
You'll never have electrons in your final equation because they should cancel out. Mm-hmm. And if they don't cancel out, you need to do something else to make them. Yeah. The order that you write these in is not important. I typically just use the same order. Yeah.
If we just did something wrong with those when they should have canceled out.
Yeah, if at this point, because we have this number 5, which we didn't actually have to do. It's very common for when you write balance the 2 half reactions that one of them's 2 electrons and one's 1 electron. And then we have to fix that before we add them up. So when... Right. They should be the same once we go to add them, but that's because we've done stuff to them. And we'll see some examples. The other ones will be more complicated. Yeah. You can't subtract things in chemical equations. You can only add them. But adding to one side versus adding to the other side is kind of like subtracting, right? But it's always adding. Just adding negatives. So I'm just going to stick with the hydrogen ion first, but I've got 2 hydrogen ions. And chromium. And then my products are H2 gas and Cr2 plus aqueous. And verifying means I'm going to look, I've got 2 H's and 2 H's. I've got 1 Cr and 1 Cr. Total of +2 charge, total of +2 charge. It's balanced. This one could be balanced without doing all of these steps. But some of the other ones, not so much. Any questions? We're going to do more examples. So here's another one. We've got iron ion and permanganate iron. We have iron 2 and permanganate ion forming iron 3 and manganese 2 ion. So I'm going to separate these into 2 half reactions. So I'm going to make 2 equations out of this. Oh, I guess this will be green. And so a good way to start that is just to put one reactant in one equation and the other reactant in the other equation. And then for the product, I'm going to choose the product listed that is most similar to my reactant. So Fe2 plus is going to go to Fe3 plus. And the MnO4 minus is going to go to the Mn2 plus. And I always try to leave a little space in front of my chemical formulas in case I need to put a coefficient in there. Now I'm going to balance with respect to mass. Make sure I've got the right number of atoms on each side. So for this one, there's 1 iron and 1 iron. This one, 1 manganese and 1 manganese, so that's good. There's 4 oxygens on this side and no oxygens on that side. So our previous experiences balancing equations, nothing like this ever happened, right? We just put coefficients in front of things. And now how do we do this? Well, we balance the oxygen by adding water. This is an aqueous solution. There's literally gazillions of water molecules in there. So it's okay to throw this into the equation. So I'm going to add H2O. These are generally at room temperature, so it's a liquid. So I'm going to put H2O in there, and now I have something I can put a coefficient in front of. Right? I need 4 oxygen atoms. I've got 4 over here. I need 4 on the right, so it must be 4 water molecules. Yeah, now hydrogen. So great, you fixed the oxygen, but you made a new problem. Now we have hydrogens that we can't balance. So you balance oxygens by adding water, and then you balance the hydrogens by adding hydrogen ions. And we do that last because that only fixes the hydrogens and doesn't mess up anything else. So I have 8 hydrogens over here. So that means I need 8 hydrogen ions on the reactant side. It feels like we're just making stuff up, but we're not. This is happening in an acidic solution, a solution of acid. What do acids do in water? They make hydrogen ions. So there's lots of hydrogen ions. We're just going to say, well, we need 8 of you to participate in this half reaction. Nope, not H2. It's H+, because this is in acidic solution. And so what we're seeing here, because in this equation up here, we've got ions without cations. I mean, we've got cations without anions, right? And so there are some spectator ions in this solution that we're not showing. We don't know what they are. It doesn't matter, so we should try not to care. And that's why there's hydrogen ions instead of hydrogen gas. There is some anion in there, like chloride or something probably. So now my second reaction is balanced with respect to mass. Now I'm going to balance with respect to charge. So my first one, I've got +2 on one side and +3 on one side. So if I add an electron to this side, then I'll have +2 on both sides. So adding electrons is a little bit like subtracting charges. And then the bottom, this one's a little bit messy. I've got a +8 from the hydrogen ions and a -1 from the permanganate ion. So that comes out to be +7. And then over on the right side, I have +2. So I need something to change by 5. And all I can do is add negatives. So I'm going to add 5 electrons to this side. Because now I've got -5 +8 and -2, and that adds up to +2, which is the same as the other side. Okay, so there was a Wi-Fi problem there, and I wrote some stuff, but it never showed up on the screen. So by adding 5 electrons, I have -5 to this side. So -5 +8 and -1, I've got +2 on the left and +2 on the right. Any questions? So both of my half reactions are balanced with respect to mass and to charge. So I'm going to erase this because this is going to get in the way. The next step in that list is make the number of electrons equal. So here I've got 5 electrons and there I have 1 electron. So I have to fix this. And I'm going to fix this by multiplying. So if this is going to take 5 electrons, then this reaction is going to have to happen 5 times. Each one is making 1 electron. So if I multiply this reaction, all of its coefficients by 5, then I'll have the same number of electrons. So 5, 5, and 5. That doesn't mess up any of the balancing I did, but it'll get me 5 electrons on the product side, 5 electrons on the reactant side. If you can't make it do that, then there's something else that you've done wrong. Yeah, so now with 5 electrons on each side, when we add them together, the electrons, poof, disappear.
And you said we should always be able to do that
Because we can always do it because we're looking at the 2 half reactions separately. And so, 1 and 5 is pretty easy. 2 and 3 comes up a lot, where you have to multiply 1 by 3 and 1 by 2 and you get 6, but you could have something super ugly like 17 and have to multiply by some huge number, but you could still do it, right? So now I'm going to add these together. So I look to see what things cancel out. Extend the line. So 5 electrons and 5 electrons. These are like spectators, but they're things that occur exactly the same on both sides of the arrow. And so I can cross them out. I don't have to include them. And then I'm going to copy down everything else. And again, I'd like to use the same order that was given in the problem. Not necessary, but sometimes it's like, well, I don't know which way to do it, so we'll do it the same way. Or maybe you want to just do it backwards because you're just ornery like that. And then over here I've got 5 iron 3 ions and manganese 2+. and 4 water molecules. And then you can go through that and verify you've got the same number of irons and magnesiums and hydrogens and oxygens on each side. Add up the total charges on each side and they'll be equal. It's a balanced equation. That's going to be really tough to do by inspection up here. Even if you do know to add in waters and hydrogens where necessary, it's still going to be hard. Any questions?
So for when you balance it, to make sure that your charges are equal,
Mm-hmm.
you can just add the +2, -1, and then +1, or is it just...
You mean down here? Looking at, are they equal down here or looking at these half reactions?
Well, when you verify it, don't we check the electrical?
Yeah, so when we verify, we have 5 positive 2 charges. So that's 10. That's +10, right? And a -1 and +8. We're like, okay, that's a total of +17. And then over here, this one will be +15 and +2 and nothing. So this is +17. So I've got positive 17 on both sides. It doesn't matter what the number is. It could be positive, it could be negative. It just needs to be the same. Because a balanced chemical equation is a bit like a teeter-totter. And the arrow is the middle of the teeter-totter. And you want it to be level. You don't want too much on one side, make that side go down, or make the other side go down. Yes?
Just clarify, so you're taking the charge multiplied by the coefficient.
Right. I multiply this charge by its coefficient because this is saying I have 5 Fe2 ions or 5 moles of Fe2 plus. And so I'm going to have 10 positive charges or 10 moles of positive charge.
I was just clarifying because, at first I was thinking you have a negative charge over O4, but it's actually over the MnO4.
Mm-hmm. Yeah, so this charge here is on the entire ion. That's a polyatomic ion permanganate. And so, and then we have no coefficient in front, so that's just going to give us -1.
How come the H complex has a good... The H2 how come it just doesn't have
Charge? Because it doesn't have a charge. Yeah. So this H2O is a molecular compound. It's neutral. It doesn't have a charge. These have charges because they are all ions. Now, there has to be some negative ions in this solution. This is ending up being a net ionic equation, so there's spectators in here. So these 5 iron guys came in with girls. We can tell that because they've got charges. They're charged up. They have a date, right? This is a girl in my chemistry land. So she must have come with some guy. It's got to be probably one of these guys. But there could be other. We could have spectator guy ions too. Or could have come in with hydrogen ions. The point is, we don't have to figure out who came with whom. We're just going to look at what got changed in the reaction. So we kind of have to get comfortable with looking at net ionic equations that don't tell us everything that's going on. They only tell us the important stuff. And we've done a lot of stuff with charges, but not everything has a charge. And the reason that the charge is shown here, and if I wrote it as a compound, like if I had the compound FeCl2, aqueous, I wouldn't write the charges because here I have the neutral compound. Together the iron and the chloride are neutral. And so here I've got H2O, all together everything's neutral there. But if I separate these ions, they have charges. If I write Fe, solid, That's just iron. It doesn't have a charge. Anybody else have any questions? Mm-hmm.
So when you're doing the checking, you're writing out the charges to make sure they're balanced on both sides, and then do you also just do like a regular check?
Yeah, you would check the atoms in the same way.
Okay.
So we could make a list, or we could just count. I've got 5 irons and 5 irons, 1 manganese, 4 oxygens, 4 oxygens, 8 hydrogens, and 8 hydrogens. So if it's not balanced here, the first thing to check was, did I copy things down correctly, right? Because if this is a 4 and you misread it and write 9, now it's not going to be balanced. So go back and make sure that you copied it correctly, and then look, are those half reactions actually balanced? Okay, let's do another one. Copper metal and nitrate ion reacting to form copper 2 ion and nitrogen dioxide gas. So here's Cu, and it doesn't have a charge because it doesn't have a charge. NO3 minus, this is a polyatomic ion, so it has a charge, and because it's nitrate ion and not nitrogen trioxide, the charge is part of its formula. Here I've got copper 2 plus ion, now it is an ion, and over here, this is not nitrite ion because there's no charge. It's nitrogen dioxide, it's a molecule with 0 charge. So again, chemists are very careful about writing charges when there are charges and not writing them when they're not. Can't get sloppy about that. So first step is divide this into 2 half reactions. I find it is easier to look at if I keep the arrows lined up. So I have 2 reactants, so I'll put 1 reactant in the first half reaction and the other reactant in the second half reaction. And the equations we make you balance in Chem 1A are going to definitely be on the simple side. There are some that get like crazy complicated, but we're not going to do that to you. So, there's 2 reactants, 1 for each half reaction. So copper is going to go to one of these. I just pick the one it's most like, which is the Cu2+. And NO3 going to NO2. Seems like that might be possible. They're similar, right? They have some of the same elements. So now I balance with respect to mass. So the first one, copper and copper, it's all good. The second one, nitrogen and nitrogen, 3 oxygens and 2 oxygens. I can't fix that with coefficients. I need to add water. So I'm going to add H2O. So I can have an extra oxygen over here. So 2 plus 1 is 3, and I've got 3 over there. I can't fix this with just the NO2 and the NO3, because if I fix the oxygens, I mess up the nitrogens. And then if I fix the nitrogens, I mess up the oxygens. And so there's just no way to do it. So we put water in here. So I fixed the oxygens, but then I introduced a new problem. Now I have hydrogens I have to balance. So I'm going to balance those with hydrogen ions. So I have 2 hydrogen atoms over here in this molecule. I need 2 hydrogens over here. So hydrogen ions. These are hydrogen ions because this is an acidic solution. It's got an acid in it. Looking at this nitrate, it's probably nitric acid. Then I balance charges. The top one has 0 on the left and plus 2 on the right. So I can fix that by adding 2 electrons to the right side. Plus 2 and minus 2 adds up to 0, which is the sum that's over there. The bottom one is 0 on the right, and on the left I have a +2 and a -1. Overall a +1 charge. So I'm going to need 1 electron over here. I have a -1 and a positive, 2 positive ones and a -1. Those all add up to 0. They just need to be the same on both sides. So my half reactions are balanced. Before I can add these together, I need to make sure that I have the same number of electrons in both of them. Because if I add these together right now, the electrons aren't going to cancel out. And I don't want any electrons showing. It's like your underwear or something. You don't want that showing in your final equation. It's happening, but, nobody needs to see it. I don't know where that came from. So 2 electrons and 1 electron. I'm just going to multiply. To make 1 electron into 2 electrons, I multiply by 2. To keep this balanced, I have to do it to everything. So I'm going to multiply that by 2. I'm going to multiply this by 2, so that becomes a 4, and a 2, and a 2, and a 2. Because I did the same thing to each species, it's still balanced. It's just doubled. Everything got doubled. Now I can add these together. So put a line down here. And I'm going to look to see, what can I cross out? Well, I'm going to cross out the electrons. The electrons should always cross out. But don't do wishful crossing out. It has to actually cross out. I don't see anything else that's the same on both sides, so I'm just going to put this together. I've got solid copper as a reactant, and I have 2 nitrate ions, and I have 4 hydrogen ions. So I took all of these pieces and wrote them here. The order that you put them in is not significant. Cu, that's not a very good U. Cu2 plus and 2 NO2s and 2 H2Os. Mm-hmm.
So if we found something else besides the electrons that were the same on both sides, that would be because it's a spectator.
Yeah, we could cross them out. Mm-hmm. Yeah, and that's going to happen in a couple slides.
Can you only add the hydrogens because this is an acidic solution?
Correct. We can only add the hydrogens because this is an acidic solution. And the next thing we're going to do is learn how to balance this in a basic solution, which is one more step, but then we end up with lots of water molecules all over the place, and so we have a lot of those to cross out. Any other questions about this one?
The mass of an electron is totally negligible when you're doing this.
The mass of an electron is negligible, but even if it wasn't, no electrons were harmed in the making of this equation, right? Because this one lost 2 electrons, and they were gained by this one, and so we actually still have the same number of electrons. Anybody else? Okay, so what if it's not an acidic solution? What if it's a basic solution? So we've talked about acids and bases. Acids make hydrogen ions in solution. Bases make hydroxide ions in solution. Hydroxide ions and hydrogen ions combine to neutralize each other and form water. Right? Remember that net ionic equation for acid neutralization reactions? So what we're going to do is we're going to balance it as if it was acidic, and then at the last minute, at the end, we're going to say, yep, correction, And we're going to add in enough hydroxides to neutralize all the hydrogen ions that we had to use. It's simpler to do it this way because it's easy to balance hydrogens with hydrogen ions because they don't have any oxygens. If you try to balance it with hydroxide ions instead, you'll be pulling your hair out because every time you fix the hydrogen, you mess up the oxygen. And we're not going to do it. So remember that this happens. So balance this redox reaction in basic solution. So we start out the same. We pretend that it's acid. Make 2 half reactions. So I minus and permanganate, I2 and MnO2. I had 2 reactants. I make a half reaction for each of them. And I just pick the product that looks the most like that reactant. Now I'm going to balance with mass first, the atoms. So this first one, I have 1 iodine here, and I have 2 over there. So I can fix that by putting a 2 in front of the I minus. I'm not worried about charges yet. Down here, the manganeses are fine. I have 1 of each, but the oxygens are not. Here I have 2 oxygens, and here I have 4 oxygens. I need more oxygen on this side, and I balance oxygens by adding water because I told you to do that. And it should make sense because this is happening in water, right? I need 2 of the water molecules so that I can get the correct number of oxygen atoms on my product side. So that fixed the oxygen but introduced a problem with hydrogen. So I look over here, I've got 4 hydrogen atoms in that thing over there, and so I need 4 hydrogen ions. To balance the mass. And this is where I remember, oh yeah, this is in basic solution. So wherever I have hydrogen ions, I'm going to add an equal number of hydroxide ions. So there's 4 hydrogen ions here. I'm going to add 4 hydroxide ions. Now I want this to stay balanced, so I have to do it to both sides. Right? The teeter-totter was level, and if I put hydroxide on one side, it's going to tip, so I have to put hydroxide on both sides. So then over here, I'm going to have 4 hydroxide ions. Everybody okay with that? Now you can do all of your simplifying at the end, or you can do some simplifying as you go along. And I prefer to simplify a little bit as I go along. So 4 hydroxides and 4 hydrogen ions, those are going to neutralize each other and make what? Water. How many water molecules? 4. And that's going to happen because we put 4 hydroxides in there on purpose to neutralize the 4 hydrogen ions. Because it's a basic solution. We can't have hydrogen ions floating around. But we have hydroxide ions. So what I'm going to do is I'm going to erase that. And I'm going to write 4H2O. Because that's what they make. And is there any more simplifying I could do in this half reaction? Anything happening on both sides? The water. I've got 4 water molecules here, and I've got 2 water molecules over there. So if I took 2 water molecules away from both sides, it would still be balanced. So I'm subtracting 2 water molecules. So that's going to get rid of all of these. So I'm subtracting 2 there. And I'm subtracting 2 here, and so I have 2 left. I have 4 hydrogens and 4 hydrogens. I have 2 plus 4, 6 oxygens. 2 plus 4 is 6 oxygens. 1 manganese, 1 manganese. It's still balanced. But I didn't have to tear my hair out with the hydroxides. Then we need to balance this with respect to charge by throwing some electrons around. The one up here, I've got 2 negative charges on the left and 0 on the right. So I'll want to put my 2 electrons on the right. In the bottom one, I've got 4 negative charges. I'm going to move him over because he seems a little lonely out there. I don't want to forget that he's there. So 4 negative charges, and over here on the left side I have 1 negative charge. So how many electrons do I need to make -1 into -4? 3. So 3 negative charges and 1 is a total of -4. And then over here I have -4. So I balance the charges out using electrons. What's the next step? Same number of electrons. So I've got 2 electrons up here and I've got 3 down there. The least common multiple is 6. So I'm going to have to multiply both of these equations so that I get 6 electrons. This can be surprisingly confusing, so I would encourage you to make a little note of what am I multiplying this one by. So I'm multiplying the top one by 3 times 3 and the bottom one times 2. So otherwise I tend to forget and I get confused. So this top one is times 3. So 2 times 3 is 6, and 1 times 3 is 3, and 2 times 3 is 6. I'm multiplying the whole thing by 3 so it's still balanced. Then the bottom, I'm going to multiply by 2. So multiplying by 2, this becomes a 6. This becomes 4. Multiply by 2. Multiply by 2. Multiply by 2. I have 6 electrons being released and 6 electrons being taken up. So now I can add this together. So 6 I minus aqueous plus 2 MnO4 minus aqueous. That's these 2 guys. And then I also have 4 water molecules. So make sure I got all of these guys. I got this one and that one. And then I'm going to write these other guys down on the right. 3I2 and 2 MnO2 and 8 hydroxide ions. And the electrons canceled out. Piece of cake, right? Complicated mess. Any questions? Are you serious? How do the charges balance on the bottom? Okay, let's check. So I have 6 times minus 1, so that's minus 6 here, and 2 times minus 1, that's minus 2, and the water doesn't have any, so that's a total of minus 8 on that side. And then over here, no charges, and minus 8. No. So, and that's something that seems to be bothering a lot of people. So what this is this is permanganate ion. It's manganese bonded to 4 oxygens, and together they all have a -1 charge. Yeah, so we don't want to take the these subscripts here and multiply charges. We could identify what the oxidation states are for the oxygen and the magnesium, or the manganese, but my guess is nobody wants to do that. Any other questions? One more example. Another basic one. So balance the redox reaction in basic solution. So we start out like it was acidic, and we write our 2 half reactions. So I've got hypochlorite ion, and I have this guy that you don't know how to name yet. And then over here, Cl minus and chromate. Balance for mass. The first half reaction, I have 1 chlorine and 1 chlorine. I have an oxygen on this side, so I need to add water to the other side so that I have 1 oxygen on each side. And then that means I have to add 2 hydrogen ions over here to balance the hydrogens. And then, because it's basic solution, I have to add hydroxide ions to neutralize the hydrogen ions. So I have 2 hydrogen ions, so I'm going to add 2 hydroxide ions. And I had it mass balanced, and so I have to do the same thing to both sides so I don't screw it up. I think it's easier to look at, and there's a lot less pluses and minuses to deal with if we recognize that 2 hydroxides and 2 hydrogen ions make 2 water molecules. That's why we put the hydroxide in there, was to neutralize the acid. And of course, this is all just us making stuff up so we can balance the equation. So 2 times 2, 4 hydrogens, 2 and 2, 4 hydrogens. 2 oxygens and 1 is 3 oxygens, 1 and 2, 3 oxygens, 1 chlorine. All my atoms are balanced. And then I could say, well, I've got a water molecule here and 2 water molecules there. I could just take 1 away from both sides. So I'm going to subtract water from both sides, and I'm going to end up like that. And then double check. The 2 hydrogens on each side, 2 oxygens on each side, 1 chlorine on each side is still balanced. I'm going to move the hydroxides over because They're looking kind of lonely out there. So I mass balanced the first one. Now I'm going to mass balance the second one. Chromium and chromium is fine. I've got 4 oxygens. So this subscript is on the outside of parentheses. So it applies to everything inside. So that's 4 oxygens and 4 hydrogens. Over here, CrO4, there's no parentheses. This 4 applies only to the letter right before it. So that's 4 oxygens. Together, the 4 oxygens and the chromium have a -2 charge. So 4 oxygens and 4 oxygens, so I just have to fix the hydrogens. I have 4 hydrogens on the left side, so I'm going to fix that by adding 4 hydrogen ions to the right side. Because that fixes the hydrogens without messing up the oxygens. But it's a basic solution, so I can't have hydrogen ions floating around. So I'm going to add 4 hydroxide ions to each side to neutralize those. It's still balanced for mass. And then to make things easier on myself later, 4 hydrogen ions and 4 hydroxide ions make 4 water molecules. So I'm going to write, 4 water molecules here instead. And then double check. Got 4 hydrogens plus 4 hydrogens, so that's 8 hydrogens over here and 8 over there. I've got 4 oxygens, and 4 oxygens is 8 oxygens, and 4 is 8. And the chromiums are still fine. Yeah, I added OH to both sides, and then I combined the H pluses and the OHs. And if you missed something, you can always go back and watch it on YouTube. It's on, my channel is Chemistry with Mrs. K, and there's a playlist for this class. So all your lecture videos are in one playlist, and the link should be on your syllabus on Canvas. So what do I need to do next? Balance the electrons. These are problems where you can get in the middle of it and you're like, oh, wait a minute, where was I going with this? So sometimes it's helpful to actually write a list. Do this, do this, do this, do this, so that you can go back and look at it. Oh yeah, next I need to balance the electrons. So I've got a total of -1 on the left side and a total of -3 on the right side. The chloride is a -1, and I have 2 hydroxides with -1. So if I put 2 electrons on the left side, the charges will add and be equal. Down here, I have 4 hydroxides, so that's a -4. And here I have CrOH4, and this minus is for the whole thing. It's not for the OH. It's for the whole thing. And so that's just -1. And then CrO4, it's kind of an ugly 4, 2-, that charge is for the whole thing. It's a polyatomic ion. And then the water doesn't have a charge. So I have -5 on one side and -2 on the other. So if I add 3 electrons, then I have -5 on both sides. And we're seeing where little tiny details, like understanding exactly what the parentheses and the subscripts and the charges, exactly what all of those mean, really important. Otherwise it's going to be impossible to do. Okay, so I have two balanced half reactions. The next step is make sure I have the equal number of electrons. And I don't. Usually you don't. So I've got 2 and I've got 3. So I do the 6 thing again. So I'm going to multiply the top one by 3 so I can get 6 electrons. And I'm going to multiply the bottom one by 2 so I can get 6 electrons. So this becomes 6 and 3 and 3 and 3 and 6. And the bottom, 2 times 4 is 8, and 2, and 2, and 8. Oh, and 6. So I need 3 of those and 2 of these so that it comes out even. All the electrons that are lost are gained by something else. Now I can add them together. And I'm going to cross off things that are the same. So 6 electrons, those should always cross out. Now there's hydroxides and waters on both sides. And you might want to fix them before you put them together, or you might want to fix them after. Because it's already, there's a lot of crossouts, right? So maybe let's just add it together and then look at a clean version. So I'm just going to copy this stuff down. 3H2O liquid plus 3ClO minus aqueous. Yeah, whatever. Plus 8 hydroxides plus 2 of those weird guys. Go back and look, make sure I got everybody. You want to leave somebody out. And a lot of times there just won't quite be room on the one line, so just kind of sneak it down there. I've got 8 water molecules over here, and I have 3 water molecules over there. So if I remove 3 from both sides, right, then this one will go away. That's not a good color. Maybe black. That one goes away. And subtracting 3 from this side gives me 5 left. Right? 8 minus 3 is 5. Is there anything else that's showing up on both sides? The hydroxides, right? So I've got hydroxides on both sides. I've got 8 on one side and 6 on the other. They don't cancel out, but we could get rid of some of them. We could subtract 6 from both sides. So if I subtract 6 from this side, they all go away. And I subtract 6 from the other side, and I get down to 2 of them. And so then I made another mess, and so let's write it out neatly, if that's even possible. You can see it'd be really easy to just make a mistake just copying it down. So I'm going to double check here. 3 chlorines and 3 chlorines. 2 chromiums and 2 chromiums. There's 4 hydrogens plus 2 is 6 hydrogens. Nope, wait. 2 times 4, 8 hydrogens, and 2 is 10, which is good because there's 10 over there. 3 plus 8 plus, let's not do that one in our heads. 3 oxygens, and there I've got 2 times 4. I've got 8 oxygens, and I've got 2 oxygens there, so that's 13. And then over here, I've got 2 times 4 is 8, and 5 is also 13. Ugh. And the charges are going to add up too. Aren't those fun?